Good. All right. Well, looks like we are ready. Good.
Okay, well, I'd like to introduce Dr. Filippenko, a longtime friend and colleague, professor of astronomy at Berkeley, got his undergraduate degree at Santa Barbara, graduate PhD at Alexei. I could go on and on about the prizes that Alex has won, the tremendous science that he's done. Many of you probably know he's also an outstanding educator. Just won the American Astronomical Society annual award for the first one. Best educator in the United States. He's also been voted the best professor. He's Berkeley number 1. But also published 800 papers, record papers on track to 8,000 papers. I'm not going to say what his H-index is. But H-index really doesn't say about the quality of the science. Outstanding science who's worked in active galactic nuclei and especially in supernovae. He also has boundless energy, and I just want to tell one story about Alex. After we discovered dark energy, we had to figure out what we were going to do with our group, the Isaac. So we decided and asked them to split our group into two. One would be the Essence, I was part of it, Brian Schmidt was part of. The other one was Adam Reese, who was the other team. I was still in Chile, and so we had one of our first students from Essence up in Seattle, Washington. And I flew up to Chile on the first day of the meeting started. I'm just dead and tired. 24-hour trip. And Alex comes down into the lecture hall, telling us about all the greatest things he's done and just won an award at UC Berkeley and all this exciting science and all of that. And so that day finished, I went back to my hotel room and decided. My shoes, I decided, well, I got to go back and fall asleep. So turn on the television, go to NPR. There's Alex on the TV screen. I couldn't get sleep. So
they're what they're saying is, I'll tell them up there in the chat room. I'll be on in a minute. Nick is speaking without the microphone. That's why you can't hear anything.
Well, then, with no further ado.
Okay, well, thank you, Nick. I actually don't remember that story. So, Nick, you have a much better memory than I do. I hope that I wasn't so enthusiastic that I kept you up and you couldn't, go and get some much needed rest, So, no, it was so much fun working with Nick all these decades and the Supernova teams. I'll tell you a little bit about the history here. Of course, you've got a number of the experts in your department, but what I thought I'd do is give a little bit of a history of the project and give you our latest results. And I know that this is a physics and astronomy department, so maybe what I have to say will be of interest to all of you to some degree. So, of course, more than a century ago, Vesto Slipher in Arizona measured galaxies, spiral nebulae, as they were called back then, to have redshifted spectra. And Edwin Hubble determined the distances of those spiral nebulae and found that the more distant ones are moving faster than the nearby ones. So here's an idealized low redshift Hubble diagram where the distance is plotted along the ordinate and the redshift, or in this case, the logarithm of the redshift, is along the abscissa. So that's a linear Hubble law, better now known as a Hubble-Lemaitre law, because Lemaitre, Georges Lemaitre, a Belgian priest and astronomer, actually figured it out theoretically 2 years before Hubble did, but didn't have as many good measurements. So I think it's high time that we finally start calling this the Hubble-Lemaitre law. This, of course, corresponds to many potentially different types of past histories and futures of the universe. The Hubble constant is basically the slope of the expansion of the scale factor as a function of time, normalized by the scale factor, so A dot over A. But in an empty universe, the expansion is simply a straight line. In a dense universe, you toss the apple up, it slows down, stops, come back. So you have that kind of a thing, but the slopes are the same at T naught now. You can have a medium density universe where it's essentially expanding at the escape speed, and it will expand forever, but just barely. Or you could have a low density universe that expands forever easily. All of them have the same slope and thus the same Hubble constant right now, but they have very different past histories, and they'll have even more different futures. They all started with a hot, dense Big Bang, but in the dense case, there's a recollapse, and in the other cases, there's eternal expansion. So we would like to know what the universe will do. And to do that, you want to look at its past history. So I'm sorry, my bottom is cut off a little bit because of the zoom thing, but it says t equals now right here. And redshift is defined by this, or 1 plus the redshift is defined by the scale factor now divided by the scale factor at the time that the light we are now seeing was emitted by the galaxy or whatever object is emitting it. Okay, so the A of t, if you're not familiar with it, is just a scale factor. You double it, you're doubling then the distances between any two sufficiently well-separated galaxies or clusters of galaxies. So there's redshift 0, A of t naught divided by A of t is now. So let's just look at some, higher redshift. Let's take redshift 1. Well, 1 plus 1 is 2, all right, by advanced mathematics. We can look at the look-back times and thus the distances the various models would predict for a fixed given redshift. And you can see the dense universe has the smallest look-back time, the smallest distance for redshift 1. Less dense universe has a bigger look-back time, a bigger distance. A low-density universe has an even bigger distance. And an empty universe that's not decelerating at all should have the biggest possible distance of an object at a given redshift, okay? So the idea is, if you measure redshifts and distances not using Hubble's law, you measure the distances in some independent way, you can then plot those two and see which of these models our universe has actually been following. So here's the observer's version of that theorist's diagram. At low redshifts, they all converge to the same slope, right? Right now, they all have the same slope because the expansion rate is whatever it is right now. That's you have no way of changing that. But at higher redshift, you can see that, oops, I did something to the screen there. For a given redshift, the dense universe has a smaller look-back time than a less dense universe. So what you want to do is measure redshifts and distances and see where you fall on this diagram. So you have to go and look at very distant galaxies. You can't just look in the linear part of the Hubble law. And determining redshifts is easy. You just get a spectrum and look at where the various lines appear. So here's a spectrum of a galaxy that's very nearby. I chose it to have 0 recession velocity. And there's a bunch of features there, absorption and emission features, that are easily recognized by a spectroscopist. Here, however, is a galaxy that's moving away at about 1/10 of the speed of light. It's the same pattern. In fact, I chose the same spectrum and I just shifted it to a redshift of 0.1. So that's easily measurable. Okay, and at nearby distances, you have to worry about galaxies and clusters of galaxies pulling on one another, but that's irrelevant when you go to the high redshifts at which the expansion of history of the universe could be measured. You don't have to worry about the so-called peculiar velocities. Okay, so redshifts are easy, child's play. Distances are the hard thing, all right? Now, there's a number of ways you can define distance. As long as you stick with the same definition, you'll be okay. You don't want to mix definitions. I'm going to be using what we call a luminosity distance. A luminosity distance, decibel, is simply a distance that satisfies the inverse square law of light. So you've got something with a luminosity L, you measure its flux, and you calculate the distance. You need to know what L is. You need some sort of a standard candle or standardizable candle. I don't like the term standard candle because, to my knowledge, correct me if I'm wrong, like Nick, there is no such thing as a truly standard candle in astronomy. Type 1a supernovae in the infrared get close, but even they are a little bit non-standard. So a calibratable candle is what you need. And what people have typically done, going all the way back to Hubble, though he did not have Hubble Space Telescope images like this, but they found luminous stars, Cepheid variables, of which there are many known examples in our own galaxy. You can determine their distances now with various satellites. We can do it individually. Back then, they kind of had to do it statistically. But the point is you can calibrate them in our own galaxy. And then you can find them in the more distant spiral nebulae. And the calibration was done by, pardon? Oh, you want to do it for as many Cepheid variables as possible to Oh, yeah. These dots are for a single Cepheid variable with a period of 5.37 degrees. This is what's called its light curve. Sorry, I sometimes forget that I'm not speaking to people who already breathe and eat this stuff day and night. But yeah, this is what's called a light curve of a typical Cepheid. Their periods go from 1 to 100 days. So, and their luminosities, vary from 100 solar luminosities to something like 10,000. They're very luminous stars. But what Henrietta Leavitt found in 1912 by looking at Cepheid variables in the Magellanic Clouds, which Harvard College Observatory had a telescope done in the Southern Hemisphere, the ones in the Magellanic Clouds are all at about the same distance. So the ones that look brighter are the more luminous ones, and the ones that look fainter are the less luminous ones. And she found this period luminosity relationship. Here's the logarithm of the star's period versus, magnitude is some measure of brightness. It's a logarithm of brightness. But you can see that there's this period luminosity relationship. So the Cepheids became a standardizable candle, even though the terminology is this dreaded standard candle, which I don't like. Okay, so Hubble then used the 100-inch telescope at Mount Wilson to look at the Andromeda Nebula, as it was called. And he was looking for novae, Latin for, nova stella, new star, but they're actually old stars that undergo an outburst for reasons I won't go into right now. But you can't see them, definitely not very easily. And then once they go off, you can see them, and then, they fade and you never see them again until maybe tens of years later. But anyway, he noticed a bunch of novae, but then he noticed one up here, which in other photographs, he could actually see. It was dimmer in the previous photographs, and then it brightened, then it faded, and then it brightened again. And so he crossed out N and realized it was a variable star, indeed a Cepheid variable star. And here is a Hubble Space Telescope picture of Hubble variable 1. I think that might be the one that's marked there. So, he saw that they were very, very faint. Therefore, the nebula is very distant. He had the distance wrong for various technical reasons, but the gist of his argument was correct. It was something way outside the confines of our Milky Way, which many had thought to have been our whole universe at the time. This thing's way out there. It's 2.5 million light years away, and it's 100,000 light years across. So it is an island universe of its own. It's a galaxy of its own. And so figuratively, Hubble expanded our view of the universe back then, all right? But then he used Cepheids in a bunch of these spiral nebulae to find that when plotted against Slipher's redshifts, which he did not, by the way, cite. Did you know that? Slipher's paper is not cited in Hubble's paper. That would be grounds for removal from a university these days, right? It's plagiarism. I don't know how Hubble got away with all this, but whatever. Anyway, so the idea is find these Cepheids and measure the distances of galaxies. Well, that's great for relatively nearby galaxies out to maybe even 100 million light years or so. But for the ones that are billions of light years away like this, the Cepheids, even the long period Cepheids, which are 10,000 solar luminosities, are not luminous enough. So you need something that's intrinsically more luminous. Enter the supernova. Okay, so here's a galaxy, and the star brightens for a couple of weeks and then fades for months. Peter Chalice, our colleague, sped things up so as not to bore you here. And there's a number of different types of supernovae. You have a number of experts on supernovae in your faculty. I'll be talking mostly about the so-called type 1As. Near the end of my talk, I'll talk a little bit about the type 2s. The 1As come from an exploding white dwarf, a degenerate star made out of carbon and oxygen. Our own sun will become such a white dwarf in a long, long time, but it won't become a type 1A supernova because it doesn't have a companion. But if there is a companion, there are several channels by which it could possibly reach or get close to the Chandrasekhar limit, roughly 1.4 solar masses, at which point a thermonuclear runaway occurs. And it could be stealing material from a more or less normal companion. It could be two white dwarfs that spiral together. There are big debates as to what is the most important channel. I think both channels produce type 1a supernovae, but certainly we're learning a lot about them. The other main type of supernova is the massive star supernova, whose iron core at the end of its life collapses, forms a neutron star, and the emitted neutrinos blow the remaining material away. Okay, so we use the 1As because they're very luminous and they're pretty standard. Okay, the white dwarf goes off in reasonably the similar manner each time. Not exactly similar though. If you plot a Hubble diagram, okay, log distance, don't worry about the m minus m thing if you're not an astronomer. It's just proportional to the log of the distance versus the log of the recession speed. Yeah, you see a Hubble law there, but it's got a lot of scatter. And that comes from the fact that the type 1As don't all occur with the same luminosity. And also there could be variable amounts of dust, interstellar smog in the way that changes their apparent brightness in a way that's not related to their distance. So there's a lot of scatter there, all right? But Mark Phillips and Mario Amui, and I know that Mario will be coming here at least for part of the time as a visiting scholar soon. They found a very interesting thing. Mark Phillips initially, and then Mario expanded on the work, and also Adam Rees, working with Bob Kirshner at Harvard for his graduate thesis, found this as well. They found, first of all, that the more luminous supernovae of type 1a take a longer time to decline. They decline more slowly. And now we actually know that they rise more slowly as well, because we have data now on the rise. And the least luminous ones rise quickly and decline quickly. And so this was calibrated from type 1a supernovae that occurred in galaxies that are sufficiently nearby that we could get Cepheid distances to them, okay? But, you know, figuring this out then, you realize that you can read the label on the light bulb. Maybe they're not all 100-watt light bulbs. Maybe some are 85, maybe some are 126, but this is a way of reading the label on the light bulb. And if you make the measurements through a bunch of different filters, then you get colors, and you can also figure out how much dust there might be in the way, because just as the setting sun looks dim, it also looks some shade of yellow, orange, or red, depending on how much ash and particulate matter you have, you know, in the sky. In California these days, the new normal is that every fall, California burns. And so the sun, even 20 or 30 degrees above the horizon, looks blood red. And I know you've had some fires here as well, but you're all familiar with this. The colors can tell you how much junk is in the way. So in particular, Adam Rees, working with Bob Kirshner and then coming to Berkeley as a postdoc, developed this multicolor light curve shape method, which was very nice. And so if you go back to this Hubble diagram and then you apply this machinery that you've determined from a couple of dozen nearby type 1a supernovae, the dispersion decreases by a factor of 3. This basically means 15%. You know, it's much, much better. And in particular, ones that were way off like this, from a combination perhaps of dust and being lower than normal luminosity, they go right down to where they should be, after doing this correction. So this is what really allowed precision cosmology to be done with supernovae, okay? So here's a type 1a, it's in a galaxy whose distance we figured out. Great. Now let's go and find them in distant galaxies. What time is it? Okay, I'm doing okay. So this is where two teams formed, first by Saul Perlmutter at Berkeley, and then Nick Sunseth and Brian Schmidt co-formed the high Z, the high redshift team, okay? And you can see the various members of those two teams. We would occasionally meet in places like Aspen. We kind of like wandering around in Aspen. In Nick's office this afternoon, I saw a photograph, another photograph of us in Aspen. And, you know, Saul and Brian were not always at each other's throats, but it was good to have this competition because of 3 reasons, really. it increased the speed with which the research was done. Both teams wanted to be first. It increased the quality, right? If one team's taking some subtle effect into account and the other one is not, then that other one looks bad by comparison. And third of all, and this was most important, the result, with which you're all familiar, was such a crazy one, an accelerating universe, that no one would have believed us had there not been two teams that came up with the result essentially simultaneously, although really the high Z team was first. Saul will contest that, but you look at the publication record and it is abundantly clear that the high Z team was first. Sorry if there's anyone here who used to be a member of Saul's team. I was the one person who was at one point a member of both teams because I started out on Saul's, but I switched to Brian's because the culture was more that of astronomers rather than high energy experimental physicists. Not that I have anything against high energy experimental physicists, but their culture is very different from that of little teams of astronomers and blah, blah, blah. So most of the data were taken at Cerro Tololo Observatory, okay? And they had this wide field camera. Nowadays, there's even wider field cameras. The Rubin telescope will be the monster of them all. But they take a picture of the sky that's roughly the full moon in area, and there nearly every blob you're seeing is another galaxy. So there are thousands of galaxies. You take 50 photographs. 3 weeks later, you repeat the process and you take differences. You can digitally, you don't even have to digitize these things. They're already digital, and you get some noise. That's okay. But there, cleverly circled, is something that looks like it might be real. And my purpose on both teams was to spectroscopically classify these objects that had been found and also get their redshifts, the redshift of the host galaxy. And so here's an optical spectrum of one of these things that we observed actually in 1999. So this was already after our announcement, but it's at a redshift of 0.455. That means a look back time of roughly 5 billion years. And to within the noise, it looks just like the spectrum of a very well observed nearby type 1a supernova. So we were very happy with those kinds of data. So here's the punchline, okay? Here are 3 type 1a supernovae spectroscopically confirmed with redshifts measured. And the punchline is that they look fainter than expected, all right? If you go back to this diagram that I had shown you, here's the diagram we're trying to populate with all these data, right? We're trying to see where does the universe actually fall. Lo and behold, it was none of the above, right? It's like your multiple choice question in your astronomy for poets class. There it is. I mean, omega matter less than 0, right? If the bottom red curve is greater than 1 and the purple curve is 1 and the black dash curve is 0.3 and the blue curve is 0, it looks like we've got a bunch of anti-gravitating matter in the universe, which would be kind of weird. But here is the actual shot of Adam Rees's lab notebook in the fall of 97 when he was on my team at Berkeley. And it was funny because Saul's team up at the Lawrence Berkeley lab, was working on the same thing at the same time, but we were trying not to talk to each other. Here's from Adam's notebook, omega matter equals negative 0.36 plus or minus 0.18. The negative sign means negative deceleration, which means acceleration. What kind of a crazy universe is this? And so when he came to my office showing me the results, I said, Adam, what did they teach you at Harvard? Didn't you learn how to measure the brightnesses of stars correctly? Go sit at Nick Snee. He does photometry well, all right? But Brian Schmidt in Australia checked the results and stuff, and we just couldn't find anything wrong. And so Einstein would be, I think, pretty unhappy with negative matter, but conveniently a century earlier, well now, but this was 1997, let's say. So 80 years earlier, he had dreamed up this cosmological constant, which is not negative mass, but it is stuff with a negative pressure, all right? And so that acts in a way opposite to that of gravity, and if it's sufficiently finely tuned, for which there was no reason, right, you'd get a static universe. Einstein didn't like this hypothesis because it implied that the density of the vacuum is non-zero, and it had to be finely tuned to give a static universe. So he happily renounced it 12 years later when Hubble and Lemaitre demonstrated that the universe isn't static after all right? So that became the interpretation, lambda greater than 0, not omega matter less than 0, all right? So let me show you the original data. It was only about a 2.5 sigma result at the time, but at some point, you got to publish. And we talked about our statistical and known systematic errors as best we could. And Perlmutter's team submitted a paper about 6 months later, and they had the same result. Okay, and you can see that systematically, at a somewhat low level of confidence, but we couldn't find anything wrong. As I said, it looks like the objects are fainter than would have been expected, even in an empty universe. All right, so that was really weird. So then you can plot omega lambda, which would be sort of this cosmological constant normalized in a way similar to that of omega matter, which is right down here. And you have these contours that we came up with, and you can see the ones from Rees et al. And Perlmutter et al. Perlmutter had more objects, but they didn't have colors, and so they couldn't correct for reddening very well. So in fact, our curves were not all that different, despite the roughly factor of 3 in number of objects. And yes, the curves intersect lambda equals 0, but most of the area is above it. And so because there were these two teams, physicists and other astronomers took this result seriously. They wanted to prove us wrong. Hell, we wanted to prove ourselves wrong. It was hard for us to stomach this as well. But these two papers came out that at least presented the evidence, okay? So that would have really surprised Einstein, who had renounced the cosmological constant upon hearing of Hubble and Lemaitre's discovery. It would be really interesting to see what Einstein would say now. Right around that time, or shortly thereafter, there were other pieces of evidence beginning to sort of be compiled. In particular, studies of what's called large-scale structure, all these voids and clusters and superclusters. To a good first approximation, they're independent of this stuff that might cause acceleration, and they were getting omega matter is 0.3 plus or minus 0.1. But inflationary cosmologists kind of liked omega to be 1. And I remember talking with Alan Guth saying, gosh, Alan, you want omega to be 1, but my large scale structure friends, Mark Davis and others, are saying that omega is 0.3. And I distinctly remember Alan saying, well, Alex, I don't know what's going on, but I'm going to stick to my prediction that omega is 1. All right. Well, okay, omega matter is 0.3. But the cosmic microwave background measurements, first with Boomerang and Maxima, then others, of course, WMAP and finally Planck, they see these little fluctuations whose physical size is quite well known because they're not very old. They're only 380,000 years old. And largely, regardless of what the universe is doing now, the early universe was doing about the same thing. And so you can calculate the typical size of these things. It's essentially the sound horizon at the time of recombination, a redshift of around 1100. And you can see that the data look a lot more like a flat universe than they do a positively curved or a negatively curved universe. So that was indicating that omega total really is 1, all right? Because the overall omega is 1 if the universe is Euclidean. So you now have these contours provided by the cosmic microwave background radiation. And you can see I'm going through this historically. We're now at 2000, 2001. So now we're 21 years ago, blackjack, okay? And all these things are beginning to intersect very nicely in this part of the diagram. You could even throw out one of them that you don't like, and the other two still intersect in about the same place. The concordance was omega matter, 0.3, omega lambda, 0.7. And then Adam Rees started finding a whole bunch of more distant ones, the higher Z team to which Nick referred. And you can see by 2004, the supernova contours alone are becoming quite tight. Now, even at 3 sigma, they're well above the lambda equals 0 line. So that's looking pretty good. And supernovae 1A plus large scale structure gave omega matter 0.28, omega lambda 0.72. The precision was comparable to that of the cosmic microwave background plus large scale structure. And omega matter equals 1 is ruled out at many sigma, okay? So that's looking pretty good. All right, so now let's fast forward another 14 years or so. The Pan-STARRS is a survey of the sky that discovers lots of supernovae. Skolnick published a very nice paper showing the so-called Pantheon survey of type 1As. And I mean, look at that. You're many, many sigma above the lambda equals 0 line. And more recently, you can find the archive. These papers are now being refereed. but here's the latest result, 2022. The papers just came out on the archive in the last couple of weeks. It's looking really good, all right? The other thing we had to consider, though, was the possibility that maybe the very high redshift supernovae are too dim because perhaps there's a lot of dust out there that's unaccounted for, maybe gray dust that doesn't cause reddening in the same way. Or maybe the type 1a supernovae exploded with an intrinsically lower luminosity back then. All right, those had to be considered. So if what's causing the supernovae at redshift 0.5 to be fainter than expected is dust or evolution, then you might say that at redshift 1, there'd be even more evidence of dust and evolution. And so the supernovae should look even fainter than expected. Whereas if this stuff is a rather late accelerating stage, which started in the last 4 or 5 billion years and was decelerating to begin with for the first 9 billion years, then you would expect them, relatively speaking, to start looking brighter again. And so Adam decided to look at very high redshift supernovae to see whether the curve is following this sort of green dashed line. In other words, at very early times when the universe was dense and small, the amount of this lambda, or as we will call it, dark energy, was small. So its cumulative effect wasn't very important. Plus galaxies were close together. So omega matter was really trying to, slow them down. So whatever this acceleration stuff is, wouldn't have mattered much in the early universe. It would have been a decelerating universe. But then as it thinned out enough and the amount of space grew, this acceleration could start dominating, okay? And so you should start seeing essentially this downturn if you look far enough. And so we found with Hubble a bunch of really high redshift supernovae around 1 rather than 0.4 or 0.5. And lo and behold, if you look at this inset in particular, the universe is accelerating for the past 4 or 5 billion years, but now you see evidence that in fact it was decelerating for the first 9 or so. And if the faintness of the supernovae here had been caused by dust or evolution, you would expect them to be at least as faint, if not fainter, at even higher redshifts. And so this study really convinced quite a few people that what we're seeing is not some other astrophysical effect, but really a cosmological effect. All right, well, the microwave background observations were becoming better and better throughout the years as well. So WMAP came along, a thing of beauty. And you also had then studies starting from this map here, let gravity take over and see what kind of large scale structure you get. Well, they got results that agreed pretty well with the observed universe if there were no lambda, but they agreed even better if there were some acceleration, at least at redshift 0.5 or less. I'm not sure why my thing is cutting off. Oh, no, it went all the way. Good. I thought it seemed to have cut off at 0.5. But anyway, studies of large scale structures seem to be indicating that there's this acceleration as well. And here's it's the millennium, what's it called? My little thing is covering it as well. It's the Virgo collaboration. Anyway, they simulate a 3D flight through the universe based on real data. And again, the simulation matches the real data better if you include late dark energy than if you don't. So when you bring all these things together, this concordance cosmology gradually emerged, all right? Dark energy, 70%, non-baryonic dark matter, 25%, baryons, 5%. Not your mother's universe, okay? Not at all, all right? So that's kind of interesting. So by this time, this is 2011 now, there's so much evidence that there's something weird going on that the leaders of the two teams and then the leader of the higher Z team, plus Adam was the first on Schmidt's team to realize what was going on. Gerson Goldhaber, the first on Saul's team to realize what was going on, passed away, unfortunately, in the year 2010. But anyway, the leaders were recognized with the Nobel Prize, and that was really fun. So dark energy seemed to be real, but in that case, though, what is it? What is it? A cosmological constant? Maybe that was our first guess, but there's not good quantitative agreement with theoretical expectations, which are like 10 to the 120th power, a truly back of the envelope calculation, you could say, although I don't see any calculation there, I just see a statement, m Planck to the fourth is roughly 10 to the 120. But Steven Weinberg calls it a bone in the throat, all right? Why is it so small out of all the things it could be? And why is it roughly comparable, 0.7 versus 0.3 to matter right now, okay? So let's look for alternatives to lambda, some other form of dark energy, let's call it. And we can parameterize it with this equation of state parameter, W, being the pressure over the energy density. And, rho goes as just volume to the -1 plus W. W is 0 for normal non-relativistic matter, right? The box simply expands. It's 1/3 for photons because the light expands as well. It's -1 for lambda. In other words, the density is independent of the volume or independent of the scale factor if you really truly have the cosmological constant, which is just an energy associated with the vacuum, rather than some weird energy, dark energy flying through the vacuum. There's that distinction. And then there's a whole bunch of models. Among the most popular are the quintessence, like the Aristotelian fifth essence, rolling scalar fields, et cetera. For example, -1/3 for cosmic springs, okay? So you can test for these kinds of things. And in general relativity, gravitational acceleration, of course, is proportional to negative of rho c squared plus 3p. That's the key there. So if p is more negative than -1/3, then that negative term will dominate over the positive one and you'll get acceleration. That's all you need is W less than -1/3. W is hard to measure. These are, I forgot, it's proportional again to logarithm of difference of distances, but here these are differences in logarithms of distances. And take it from me and from Nick, doing photometry, that is measuring brightnesses to 1/100th of a magnitude, is hard work. Okay, there are all kinds of systematic effects that can bite you in the butt, so to speak, and you have to go out to pretty high redshifts to start seeing differences that are appreciably different from zero. Nevertheless, and I'm skipping a lot of history here because I know that time is limited and I want to have time for questions. Again, you can look up, these papers have just been posted on the archive. Here's the latest and greatest Hubble diagram by the Pantheon Plus group. And you can see it goes all the way out to redshift 1 and beyond. Now the deviations from the Hubble law are minuscule. This is just a thing of beauty. And so here's some of the things they can derive from it. They can get W versus omega matter. Here's their 2018 sample. Here's their 2022 sample. You get these banana diagrams. Okay, they're somewhat constraining, but the W and the omega matter could be still a range of different values. However, when you combine this with cosmic microwave background measurements or baryonic acoustic oscillations, essentially clumps in the distribution of galaxies on large scales today that are left over from from when the universe was 380,000 years old, and you can see the clumping in the cosmic microwave background radiation. When you add those constraints, you get some pretty tight values now on what W and omega matter are. And you can see that within the uncertainties, W is consistent with -1, which, that would be the cosmological constant, but you would have to show it's exactly -1, 0.000000000 to be convinced that it's the cosmological constant. So I like to say that we will never know whether it is the cosmological constant. If it is, we can only know that it's not if we ever measure something that significantly deviates from -1. But so far the data are consistent with -1, which is pretty amazing. The other thing you want to see is the derivative, and the time derivative can be hard to measure, but here's one way to parameterize W as a function of time. W of A, the scale factor is W0 plus W of A times 1 minus A. Okay, so for lambda, W0 would be -1 and W of A would be 0. All right, so what does Pantheon say? Well, there it gets kind of interesting. The error bars are pretty big. They nominally differ from the expectation of the cosmological constant, but only at 2 sigma. So you you could say it's consistent with the cosmological constant. Just depends on your spin or what you like, right? I mean, minus 0.65 is 2 sigma away from 0. Interesting, you know. Yeah, well, who knows? Maybe it's not the cosmological constant. So is dark energy really the cosmological constant? We don't know. The data are consistent, but we're still not sure. So a way to approach this problem somewhat independently is to measure the current expansion rate really, really well. And you might say, well, but you know, this only makes a difference long ago. So what do you care what the current expansion rate is? It turns out that for slight differences in the slope here, you actually have, you know, differences in the model back here, but you can predict kind of, you know, what might happen in the future. So it's not all just about measuring the past. Let's measure the slope here really, really well and try that approach, okay? So here's the most recent surprise. And many of you have heard of this, and you know, it's been growing over the years, but we just had a paper accepted where it's become really, you know, it's a 5 sigma result, as I'll show you. So people are taking it very, very seriously. It's called the Hubble tension. What's the tension? All right, so you now have the Planck map, which is a true thing of beauty. And from these fluctuations and using the standard cosmological model, okay, the lambda CDM model, in other words, there's no clear evidence that the dark energy differs from lambda. So let's just, as a simplest hypothesis, the null hypothesis is that it is lambda. That's the standard cosmological model now. And you've got this incredible power spectrum, which, you know, is just amazing, actually. I mean, that point is a bit off, kind of weird, but, you know, you don't have many samplings of a dipole. So, all right, that's the way it goes, or a quadrupole. So the point is this. It's what I said qualitatively earlier. You know the sound horizon physical scale, all right? You know that quite well. And you can measure the angular diameter distance, all right? And from that, you can basically predict what today's value of the Hubble constant should be, all right? That's the basic thing, assuming this standard concordance cosmology. And the result that they predict is that H naught is 67.4 in these crazy units, kilometers per second per megaparsec. A megaparsec is 3.25 million light years. Who cares? Doesn't matter. But look at that error bar. It's just tiny. All right. Well, for years and years, people have been measuring the local value of the Hubble constant. And, you know, that was one of the reasons the Hubble Space Telescope was built. It was one of the Hubble key projects led by Wendy Friedman. And, you know, you look at various papers over the years and sort of 70 to 75 plus or minus 4 to 7 kilometers per second per megaparsec. So, you know, that's not a clear conflict. 70 minus 4 is 66, you know. 75 minus 7 is 68. So, you know, unclear. Error bars are large, and the error bars themselves were uncertain. All right. So, I don't know, call it 2004 now. 18 years ago, 18 or 17 years ago, Adam Rees formed SHOES, a tortured acronym, Supernovae and H naught for the equation of state of the universe, something like that. It's a tortured acronym, but it's got, you know, representation of people here. You know, its labels are cut off, but Lucas Macri and Samantha Hoffman. And the goal was to eventually measure H naught, the current local value, to a precision of 1%, okay, through direct parallaxes with first Hubble and now Gaia of Milky Way Cepheids. Recall in the early days, you could only get statistical distances for them. Cepheid calibration of supernova 1A hosts and the supernova 1A Hubble diagram. And, you know, so here are some of our hosts, and there's a bunch of our light curves. We have very strict criteria for which supernovae are good enough to be included in the sample. They have to be reasonably unextinguished by dust. They have to have been caught early so we get the rise and we really sample the maximum well. They have to be more or less normal. There are weird ones at the either end of the Phillips relationship, which we try not to use, although we think we can calibrate those. Still, people might criticize us if we don't use the normal ones. So it's really great. And the way we calibrate those is by the tried and true method of finding Cepheids. Okay, so here's one of these supernovae in a ground-based picture, supernova 2007 AF. So there's a ground-based picture. You're not going to find Cepheids in that. But in the Hubble picture, you know, there are a bunch of resolved stars, and the Cepheids, if you didn't recognize them, are circled here. And you can measure their periods and thus know their luminosities. The other thing you want, though, there's a bit of a metallicity dependence. And so my, besides contributing to the light curves, my contribution to this project was that at Keck, we could take an ultraviolet, ground-based ultraviolet image of a galaxy, see where all the ionized gas clouds are, H2 regions, and then measure their heavy element abundances by taking spectra. All right, so we now have then this three-rung distance ladder, geometrically calibrated first rung, the type 1a supernova host galaxies calibrated with the Cepheids, and then you go out to the higher redshifts, but not so high that you have to take deceleration into account, or acceleration, I should say, into account. But there's the sort of relatively nearby distant Hubble diagram. All right, and you can see the history of what has been happening. Okay, so here we are. The WMAP things finally became available, 2001, big error bars. Oh, sorry, here's WMAP. Here's the local measurement error bars. This is like from the Hubble Key project. And so for a while, as I said, you couldn't tell what was going on. But starting in 2012, 2013, this tension was emerging. There's Shoes, a series of papers, and the tension grew from 2 sigma to 3 sigma to 4 sigma. And people are getting worried. Now, I've been giving this talk in various forms for years and years, and people would always say, oh, it's like, it's some weird thing, and it's just a statistical fluke, and it means nothing. And I said, well, that's what we thought maybe back in 1998, and it was an accelerating universe back then, so maybe luck is with us, and we found something interesting in the universe again. All right, so this is on the archive, just been accepted. In fact, here are 42 host galaxies, nice spiral galaxies with young stellar populations, lots of Cepheid variables. And we give the result, right? 42 calibrators, and that's a very appropriate number for anyone who's familiar with Douglas Adams's Hitchhiker's Guide to the Galaxy, right? Deep thought sits around thinking for millions of years, 5 or 10 million years, and then it comes up with the answer to the question of life, the universe, and everything, and it's 42. So I think that's why we chose 42 calibrators, but I kind of doubt it. Anyway, what is the answer then? Here's our final answer. 70, what time is it? Okay, getting close. 73.04 plus or minus 1.04. Wow, folks, here's the Planck thing. This is now 5 sigma. This is even in high energy physics, it's a discovery, all right? Something is amiss. And we have smaller uncertainties than before, and we took great pains to understand the uncertainties, much better than before. So this is really weird. And if you take it seriously, by the way, the age of the universe is only about 12.9 gigayears, not the 13.8 plus or minus 0.01 that the microwave background people would have you to believe. I mean, if you believe there's statistical errors, yeah, it's 0.01 error in 13.8, but there's something going on. If you adopt these parameters, then the age is only more like 13 billion years. All right, well, you want to test this with as many ways as possible, and I'll show you some of the ways, I'll briefly mention them, but because I had a postdoc until a couple of years ago, Thomas de Gege, using type 2 supernovae to try to measure distances. These are the supernovae that come from red supergiants, which are about the size of Jupiter's orbit, okay, and they have this iron core, blah, blah, blah. Well, they're totally non-standard. They're far more non-standard than type 1a supernovae. This is brightness goes up, luminosity is up there, and here are their light curves. So they're totally, crazy. But Mario Amui and Filippenko noticed, 2 decades ago, an interesting correlation that the more luminous type 2 supernovae also are expanding more quickly, okay? And so when you take that into account, again, using a bunch of type 2 supernovae in galaxies with Cepheid calibrated distances, then the scatter goes down quite a lot. It's still not where type 1As are, but this is like the early days of type 1As. This is pretty good considering the scatter was more like 1 magnitude without correction. So in a series of papers, Thomas de Gege has made a very nice type 2 supernova Hubble diagram. And most recently, we've played the same trick as with Shoes we measured Cepheid variables in the hosts of 13 now type 2 supernovae. And so we now have 13 points on this lowest rung, which is the anchor for the more distant so-called Hubble flow supernovae. And this now just appeared in the archive as well. And our result is 75.4 plus or minus 3.9, okay? So this agrees with supernova 1A. It's significantly more uncertain, but that's because type 2s are not yet, well, they're not as good as 1As and they're not as well developed. But you know, we'll get more data with time. And other completely independent methods confirm the tension. So I just show some of them here. Here's Reese Cepheids. You can use masers in some galaxies. You can use the rotations of galaxies, gravitational lenses. Quasars are strongly gravitationally lensed by an intervening galaxy, and the light paths are different lengths and go through different gravitational potentials. So the quasar appears to vary at different times. If you measure that, you then get the scale of the whole thing. That's how that's done. Surface brightness fluctuations in galaxies. I'm running out of time. Type 2 supernovae, and then Thomas, with other collaborators, is working on near-infrared Hubble diagram, and they apparently have a paper close to submission. I've not seen it. I'm not a collaborator on that, but they have really quite nicely small error bars. But all those things agree, basically. You know, there are many agreements at low redshifts, and there's this gigantic review, more than a year old at this point, but still, it was an amazing review of all the nearby methods and all the early universe methods. And you know, maybe something, you know, maybe the CMB people are wrong in their data analysis. I kind of doubt it. Maybe we're all wrong at low redshifts. I kind of doubt it. So what are the possible explanations? Okay, well, you know, it's possible that one of us or the other are wrong, but I'm doubting that more and more. I think it's an interpretation. General relativity wrong? Boy, that would be pretty exciting if true. I'm not saying that's what's going on, but it's a possibility, right? Because all this analysis is based on accepting the general theory of relativity, right? A non-zero curvature of the universe would do it. I'll show you a diagram in just one second. We could be in a large low density bubble. Again, I doubt it because of various measurements. I doubt the curvature, by the way, as well. Dark matter might be behaving weirdly, interacting with light in some weird way. Dark energy might be becoming stronger. There might be a very light subatomic particle that affects the expansion of the early universe. Or probably my favorite now, according to various friends I talked to, is an early dark energy, earlier than the time of recombination. That would have the same effect, by the way, as a new light subatomic particle. If you make early expansion faster than you thought it was, then recombination occurs at an earlier age, and the sound horizon is smaller. They use their assumed sound horizon to propagate their observations forward to today. If the actual sound horizon were smaller, then of course their prediction for H0 would be wrong. So it's not that they did anything wrong in their data analysis or anything. They just didn't take into account something for which there wasn't any evidence beforehand. That's the idea, okay? So, here we justify these things. For example, adding a relativistic particle, delta n effective of only 0.4 gets you most of the way there. Delta of W0 of only negative 0.08 gets you, halfway there. Early dark energy could do it. Yeah. But, here are all these local universe measurements, and here are all the things that are one way or another related to the CMB. So stay tuned. I think it's really exciting, and it's so much fun that I've been involved in this. So thank you very much. I hope there's time for questions despite the late start. Look at that, 5 o'clock. Yeah. Yes.
So, this last experiment.
Yeah. Yeah, that's this thing here, basically. Yeah, so, yeah. So the question's being asked is the early dark energy boost, did it happen before regular inflation or after? It would have been after regular inflation, but before recombination. Here's the redshift. 10 to the 4, 10,000. Recombination was at around 1,000. Okay. Inflation that we all love, not all of us, but I'm quite enamored of it, was 10 to the minus 35 seconds. Okay, so I don't know what redshift that corresponds to, but it's some gigantic redshift. It's nearly infinite. So this would be some dark energy that would have acted in that intermediate time. And if today's dark energy is not the vacuum of space, but some scalar field or something, that's one example. And early inflation was another example, because it changed with time, so it was not the vacuum energy. So that would be two historical precedents in a sense. If there was a dark energy type thing twice, why not a third time? Or some relativistic particle, but it would have to be something like a sterile neutrino, because we know quite well that there can only be 3 flavors of neutrinos. Otherwise, that take part in Big Bang nucleosynthesis, because otherwise you mess up the abundances of hydrogen, helium, and their isotopes. There's also only 3 interacting neutrinos, measured in laboratories and stuff. So my particle physics friends, I don't know, maybe I should ask a poll here. They don't like the relativistic particle explanation. They don't like a 4th neutrino. Anyone here like a 4th neutrino that's sterile or something? But that was the explanation for a while. But now that the tide has shifted, I would say, toward this early dark energy. Just because you cannot, at this point, ignore that a bunch of methods at low redshifts give a systematically, at 5 sigma, higher value than anything having to do with the early universe. So some assumption, I think, has to be wrong in propagating their data to their prediction of today, 67.4 plus or minus 0.5. And a simple assumption that could be wrong is simply that their assumed physical scale for the sound horizon was wrong. And early dark energy could do that. We don't have, and there have been some papers recently where some evidence is claimed for early or dark energy in the CMB data. I have not, I'm teaching a big class this semester, and I'm not enough of a CMB expert to really even understand those papers. I don't know, Nick or anyone here, have you read those papers where there's some people who are claiming evidence in the CMB, but you can find people, I'm not saying that they're disingenuous or anything, but there are people who in the CMB data claim they find matched circles and stuff to have Penrose's, information from pre-Big Bang and things like that. And most people doing statistical analyses of the CMB show no matched circles, And then there are people who say that the one really cold spot in the CMB shows that we live in some sort of an anomalous, weird universe. Well, there's a 5% chance, it's 2 sigma, that in any observed volume, you will have such a cold spot. 5% to me does not cry out for new physics, right? But you get these differences in philosophy. Now that people are seeing a 5 sigma difference, they're coming up with ways to try to see evidence for it, but I have not myself, to my satisfaction, evaluated whether they've done a thorough job or whether they're just groping and trying to find something in the data that might support early dark energy, but maybe someone here has analyzed their papers. But it is something you're seeing on the archive now, people claiming that there's this evidence. Yes. Are we trying to get, the question is, now that there is this discrepancy, are we going to get together with the teams to try to figure it out? Yes and no. At conferences in the past 2 years, mostly over Zoom and stuff, let's hope there's not another spike. It's been discussed. I think the CMB people for many years thought that there's something wrong in those of us who are doing the low redshift universe. I think that argument is very difficult for them to make now. The type 1a supernovae alone have reached 5 sigma, and all these other methods of doing it at low redshifts give a consistent result. So I think it's very difficult for them to argue that we're all doing something wrong. A low density bubble, You could argue that, but you can make measurements now in these giant galaxy surveys. You go out to very big distances, and we just don't appear to live in a sufficiently low density bubble to change the Hubble constant by, what is it, 73 minus, say, 67. So 6 out of 70 is roughly 9 or 8%. You need a pretty big low density bubble that would be pretty obvious, I think, in the different galaxy surveys. But a low density bubble would have a larger than global Hubble constant, but I don't think that's the case. So I think the microwave background people are beginning to realize that the ball is sort of in their court. It's not necessarily, as I said, that they've analyzed their data. There are some weirdnesses. The northern hemisphere data don't quite are not quite consistent with the southern hemisphere data. So there are some weirdnesses there, but I'm not a CMB expert, and most of us who do low redshift work are not either. So it's not really even for us to say, aha, it's obvious what you did wrong. I mean, the experts need to figure it out. And if they keep trying for another year or two and don't find anything that they did wrong in their data analysis, then I would say it almost certainly has to be an astrophysical or a cosmological effect. And all these other things, the reason I sort of italicized, I did these by the way, I did these in order of what I personally think is the likelihood. I think it's very unlikely that general relativity is wrong. I think it's very unlikely that there's a non-zero curvature because I think the arguments for inflation or something like inflation are pretty overwhelming. Then I put large low density bubble. Dark matter behaving weirdly. Well, I mean, we don't know what dark matter is. So there, it's sort of like, well, great, wonderful. You tell me. But then, dark energy, I showed you the Pantheon result. It goes the wrong way, by the way. They had W naught at negative 0.5, let's say, something like that. You need some sort of a phantom energy that's getting stronger, which actually violates the weak principle. I'm having the weak energy principle. But in general relativity, that's not fatal. You can violate it. Energy just gets created out of nothing. But that's what something more negative than a W of -1 would be, a phantom energy. But if anything, the data are on the wrong side of -1, but still the uncertainties are big. So maybe dark energy is becoming stronger. I kind of doubt it. But that's why I like these two. And I like this one the most up until about a year ago. And I talked to my particle physics friends and they don't like that one. And then, everyone's sort of talking about this one now. Yeah. There's a question back there, I think. Yes. Yeah. The interesting question or comment is, is there the possibility that at different times in the history of the universe, different combinations of these explanations may have played a role? I guess so. Sure. But if you're going to go as far as to say that general relativity is wrong, then probably that would suffice and you wouldn't have to invoke any of these others. Or even invoking even one of these is sort of, it's disturbing to many of us if even one of these were invoked. And so I think the strongest argument for rejecting or not seriously considering a combination of them at this time is that then more than one thing would be distressing for us. And one is bad enough, so why invoke two, especially if one of them were as extreme as saying, what, folks, general relativity is wrong, right? But, dark matter behaving weirdly or there being, early dark energy, yeah, maybe both of those is what's happening. That's going to be harder to notice, I think, right? Because then you need a lot of measurements over many, many different redshifts to see changes, right? In getting the acceleration, we, to first order, measured the expansion history of the universe. 5 billion years ago and now. And the first order result was that it's expanding faster now, not more slowly. To get W and all those things, we had to fill in that curve more. And to get, for example, the early deceleration, we had to go far enough back to see where A of t versus t was sloping, concave downward sort of, right? So it's gonna, I think it'll take a lot more precise data to disentangle a combination of these possibilities, but it's certainly possible that there's more than one. Yeah. Yes. Oh yeah, the evolution of the error bars is a function of time. It's really fascinating to look at, isn't it? Yeah. Here it is. Yes. Well, so this is 2013 would have been Planck. So you go from WMAP 9 in 2013 to Planck 2013. So WMAP lasted for 9 years. Their error bars got smaller and smaller, right? But then Planck, well, I mean, I didn't have it here, but you can find online, they show that the whole sky and with a diagonal through it, and half of it is WMAP and half of it is Planck. And the difference in the quality is it's just breathtaking. So Planck, at least statistically, is giving you really great results. There's still possible calibration issues, right? And there I'm not expert enough to know what they're dealing with, but at least statistically, their error bars gave this almost, I was incredulous, 67.4 plus or minus 0.5. If and my incredulity will have been vindicated if the true answer really is 73, because it'll show, not that they did garbage, but the saying, garbage in, garbage out. If their sound horizon assumption was wrong, then it doesn't matter how great their data are, their extrapolation to now and to this, you look online and every newspaper article, it says, the universe is 13.80 plus or minus 0.02 giga-years old. And we're saying it's 12.9, right? So I'm not a huge fan of Donald Rumsfeld, but he did have one interesting thing to say. I think it was regarding Iraq or something. There are the known unknowns and there are the unknown unknowns, right? And there are such things as unknown unknowns, right? And yeah, so, but that's that jump. And then the shoes thing, our value has changed very little. Our error bars have been shrinking over the years. Yeah, that's an interesting point that's being made, is that for those online, the error bar of the Planck, especially even the first one, well, these were 1 sigma, so you could say, okay, that's okay. But this one is really small. Of course, the error bar of WMAP is big. So you could say that these teams are not at odds with one another to within the uncertainties. It's only 2 sigma. But yeah, the Planck uncertainty to me just looks ridiculously small, because I cannot believe that they have such a good handle on their systematic errors. But who am I to say? They probably will say, these 1A people, they don't have a handle on systematic errors. White dwarf explosions could evolve with time. I say, fine. That's why we welcome all these other techniques. Holy cow was the strong gravitational lensing. My colleague Changpei Ma has been involved in the Blakesley et al. Surface brightness fluctuations. That's a technique where, for a galaxy, if you look sort of at sort of a seeing disk, and there are not many stars in it, root n over n will be a big number if it's nearby. But if it's far away, you're looking at lots and lots of stars, and root n over n is a smaller number. So just by the granularity of a galaxy, you can kind of tell its distance. And they came up with, I think, I forgot which one is theirs. I don't know which slide it is, but anyway, it's, where is that? Yeah, it's right here. It's, well, no, I don't remember what slide it is, but anyway, they have a, oh, it was forward, right? Sorry, it's this one right here. I've got it just so you have something to stare at. in the last seconds here. Independent methods. Okay, there they are, right? So Blakesley, that's the surface brightness fluctuations. They, and then even Thomas de Gégé's work, pretty big error bar, but again, it's completely independent of 1As. And you may say, well, it's supernovae and they're no good. Okay, we'll take surface brightness fluctuations, take gravitational lenses. Right now, I don't take gravitational waves for H naught that seriously. I take gravitational waves themselves very seriously. Fantastic. With 100 of these things that have an optical counterpart, they might become competitive. Right now, it's an interesting exercise. I even had one of my grad students do this exercise for a source that had no optical counterpart, but you could do a Bayesian analysis with the redshifts of the galaxies in that general field of view. And you could say, well, here's the distribution of possible distances and blah, blah, blah. So, but, despite what gravitational wave people say, merging black holes are not going to do it. They really need neutron star binaries, or at the very least, neutron star black hole things. And they need 100 of them. That's going to take a while. And all these techniques are going to get better too. So I'm not poo-pooing gravitational waves, but when they say that, they're going to be competitive for H naught, it's going to be a while. And it's not like everyone else is going to be standing still. But I welcome that completely independent method that doesn't even rely on electromagnetic waves other than getting the redshift. Yeah. Great. Thank you very much. Yeah, super. I guess we have some refreshments and stuff now, right? Or something there. Oh, that's tomorrow after the Mitchell. Yeah. So for those interested, I'm giving the layperson's version of this talk tomorrow at 3 o'clock as the Mitchell lecture. And it's the same content, but none of the technical details, okay? Yeah. Hello.